It's 2:47 a.m. A blip appears on a screen. No identification signal, no flight plan filed, no radio contact. In less than 90 seconds, every radar operator in a 500-mile radius knows something is wrong. In less than 4 minutes, fighter jets are already in the air. And in less than 12 minutes, that unknown aircraft is no longer unknown. This isn't a movie. This is exactly how modern air defense works every single day, across dozens of countries worldwide. And today, we're going inside the system that makes it all possible. Now, before you think this is just a bunch of technical jargon, stick with us in this video. We're going to use analogies, real-world examples, and a step-by-step breakdown so that by the end of this video, you'll understand what radar operators see on their screens, what decisions get made in those high-pressure moments, and what happens when a nation's airspace is violated. This is one of the most fascinating and underappreciated systems in modern defense. Let's get into it. What is radar, really? Alright, first things first. What even is radar? The word radar is actually an acronym. It stands for radio detection and ranging. And here's the simplest way to think about it. Imagine a bat in a pitch-black cave. The bat can't see anything. So what does it do? It screams. It sends out a pulse of sound in every direction, and then it listens. When that sound hits a wall, or a bug, or another bat, it bounces back. The bat hears the echo and instantly knows something is there, and based on how long the echo took to come back, it knows how far away that something is. Radar works on the same principle, except instead of sound, it uses radio waves. A radar station sends out a powerful pulse of radio energy. That energy travels at the speed of light, 186,000 miles per second. When it hits something, a bird, a cloud, an airplane, some of that energy bounces back. The radar antenna catches that returning signal. And from that tiny little echo, computers calculate three critical things. 1. Distance. How far away is that object? This is calculated by how long the signal took to travel and return. 2. Direction. Which way is it? The antenna is constantly rotating, so the bearing of the return tells operators the angle. 3. Altitude. How high is it flying? More advanced radar systems use elevation scanning to determine this. Put all three together, and you've just pinpointed something in the sky. Now, here's where it gets interesting. Military radar isn't just one type of radar. It's a layered system, almost like rings of defense, each one designed to catch different kinds of threats at different distances. Let's break those layers down. The three radar layers of air defense. Think of military air defense like the walls of a medieval castle. The further from the castle you catch an enemy, the more time you have to respond. Air defense works the same way. There are three main layers. Layer 1, long range, early warning radar. The first layer is called early warning radar, and its job is simple. Detect anything and everything as far out as possible. We're talking ranges of 300 to 3,000 miles in some systems. The most famous example of this is the American NORAD system, the North American Aerospace Defense Command. NORAD uses a network of giant ground-based radars, satellites, and even radar-equipped aircraft to monitor an enormous bubble of airspace around North America. When an aircraft takes off anywhere in the world that could pose a potential threat, NORAD often knows about it before it leaves its own country's airspace. But early warning radar has a limitation. It doesn't tell you what something is, only that something is there. That's where Layer 2 comes in. Layer 2, identification and tracking radar. Once a contact is detected, mid-range tracking radars take over. These are more precise systems. They can follow a specific target continuously, mapping its speed, heading, and flight path. Think of early warning radar as a security camera that sees movement in your yard. Tracking radar is the spotlight that follows it. At the same time, operators use a system called IFF. Identification, friend, or foe. Here's how IFF works. Every commercial aircraft and every friendly military jet carries a device called a transponder. When a radar signal hits the plane, the transponder automatically sends back a coded signal that says, in essence, "I'm friendly, I'm flight UA 447, here's my ID." It's like a digital password challenge. Now, what happens when a contact does not send back that password? That's when alert levels go up. That aircraft is now classified as unknown, and every radar station in the region gets notified. Unknown doesn't automatically mean hostile. It could be a malfunctioning transponder, a private pilot who got lost, or a medical emergency, but it also could be a foreign military jet probing defenses. So operators escalate. They try radio contact. They compare the contact's position to known flight corridors. And if nothing checks out, they scramble interceptors. Layer 3, fire control and weapons radar. The third layer is the most precise and the most lethal. Fire control radar is designed for one purpose: guiding weapons to a target with absolute precision. Where early warning radar sweeps broad areas and tracking radar follows a contact, fire control radar locks onto a specific aircraft and never lets go, feeding continuous targeting data to surface-to-air missiles or guiding fighter jets into firing position. This is the radar that the pilot of that unknown aircraft dreads most, because if a fire control radar has locked onto your plane, you'll know it immediately. Warning systems in modern jets scream when they're being painted by weapons-grade radar, and at that point, you have very few options. Now let's put all of this together. At this very moment, hundreds of radar stations around the world are awake. Operators are watching screens. Computers are processing thousands of radar returns every second. Most of what they see is completely normal. Commercial airlines, cargo jets, military training flights. But every so often, something doesn't belong. Here's a real-world scenario to make this concrete. Let's say a foreign military aircraft takes off from a base across the sea and starts flying toward another country's airspace without filing a flight plan. Minute 1. Long-range early warning radar picks up a contact. It appears on screens at the National Air Defense Headquarters. Computers begin automatically logging its position, speed, and heading. Minute 3, the contact fails to respond to IFF challenges. It's now classified as unknown. An alert is automatically sent to the nearest airbase. Minute 5, radio operators attempt contact on international emergency frequencies. No response. The aircraft is still heading toward restricted airspace. Minute 7, 2 fighter jets are ordered to scramble, military language for take off immediately. Pilots who are on standby, already suited up, sprint to their aircraft. Minute 10, the jets are airborne and climbing fast. Ground-based tracking radar hands off the unknown contact's position directly to the pilot's onboard systems. Minute 12, the fighters are within visual range. They pull up alongside the unknown aircraft, close enough for the pilots to see each other. This is called a visual intercept, and it happens more often than most people realize. The goal at this stage is identification. Is it hostile? Is the crew in distress? Is it deliberate provocation? What happens next depends entirely on the situation, the rules of engagement, and what that aircraft does. Now let's talk about the scenario where diplomacy fails, where that unknown aircraft is confirmed hostile, has already taken aggressive action, or has violated airspace without any intention to respond. This is where radar shifts from a detection system to a weapons system, AIR-to-air combat. The fighter's radar, modern fighter jets carry their own powerful radar systems built right into the nose of the aircraft. A plane like the American F-22 Raptor or the F-35 carries what's called an Active Electronically Scanned Array Radar, or AESA. Here's the simple version of what AESA does. Instead of mechanically rotating a single radar dish, an AESA radar uses hundreds, sometimes thousands, of tiny electronic transmitters that each fire independently. The computer can steer the radar beam electronically in any direction almost instantly. The result? A radar so advanced it can track up to 100 targets simultaneously, detect stealth aircraft that older radars can't see, switch between radar modes in milliseconds, be nearly impossible for an enemy to detect or jam. When a pilot locks onto a target, the radar begins feeding a constant stream of data to the missile, and this is where modern air-to-air missiles become truly remarkable. Take the American AIM-120 AMRAAM, nicknamed the Slammer by pilots. Once fired, this missile doesn't need the launching aircraft to keep tracking the target. It has its own radar seeker in its nose. The launching aircraft guides it to the general area with data link commands, and then, in the final phase, the missile's own radar takes over, homes in on the target, and detonates. This is called fire and forget. The pilot can turn away, evade, or engage other targets the moment the missile is launched. The entire engagement, from radar lock to missile impact, can happen in under 20 seconds. Surface-to-air missiles, when the ground fights back, but fighter jets aren't the only weapon in the arsenal. Some of the most sophisticated anti-aircraft systems in the world never leave the ground. The Russian S-400, the American Patriot system, and Israel's Iron Dome all use ground-based radar to detect, track, and destroy airborne threats without a single pilot involved. Here's how a ground-based air defense system typically works. Step 1. Search radar constantly scans the sky, looking for any contacts. Step 2. When a contact is detected and classified as hostile, the system automatically cues a tracking radar to lock onto it specifically. Step 3. A fire control computer calculates a precise intercept trajectory, not where the target is now, but where it will be by the time the missile arrives. Step 4. The missile launches. During flight, the ground radar continues tracking both the missile and the target, sending course corrections to the missile in real time. Step 5. In the final seconds, some systems switch to the missile's own seeker, radar, infrared, or both, for the kill. The Patriot missile system, famously used during the Gulf War, the Iraq War, and more recently in Ukraine, can engage targets flying at speeds exceeding Mach 5. That's 5 times the speed of sound. Think about what that means. A missile traveling that fast leaves almost no time for any evasive maneuver. The radar has to be precise. The intercept calculation has to be flawless. And the entire sequence from detection to detonation can be, in some cases, fully automated. Now, you might be thinking, if radar is this powerful, why do countries still invest in stealth aircraft? Great question. Stealth technology doesn't make an aircraft invisible to radar. That's a common misconception. What it does is make the aircraft extremely small on a radar screen. So small that it can appear like noise, like a bird, or simply get lost in the clutter. A standard commercial airliner has a radar cross-section, a kind of radar size, equivalent to a large building. An F-22 Raptor in stealth configuration has a radar cross-section roughly the size of a marble. That tiny return is incredibly difficult to track, lock onto, and engage. And then there's electronic warfare, jamming. Modern aircraft carry jammers that can flood enemy radar with noise, confuse tracking systems, or even send false signals. In some cases, a jamming aircraft can make it appear as though there are 10 planes on a radar screen when there's really only one. So what's the countermeasure to stealth and jamming? More radar, different radar. Low-frequency radar systems, like Russia's Nebo-M, are better at detecting stealth shapes because longer wavelengths interact differently with angular surfaces. Bistatic radar systems, which separate the transmitter and receiver across different locations, are much harder to fool because there's no single point to jam, and passive radar, which doesn't transmit anything at all, but instead listens to existing signals like cell towers and TV broadcasts, is nearly impossible to detect or jam because it never announces itself. The radar arms race is ongoing. Every advancement in stealth triggers a new advancement in detection. Every new jammer is met with a new counter-jammer. We've talked a lot about the technology, but here's what often gets forgotten. Behind every radar screen, every missile system, every intercept, there is a human being making a decision. In a world of automated targeting, artificial intelligence, and fire and forget missiles, the question of who authorizes an engagement is more important than ever. Most modern military systems are designed with human oversight at the decision point. A radar might lock on automatically, a computer might calculate the perfect intercept solution, but in most democratic nations, a human officer, under strict rules of engagement, must authorize the actual firing of a weapon, because radar systems, as advanced as they are, can be wrong. In 1988, the USS Vincennes mistakenly shot down Iran Air Flight 655, a commercial airliner, after its radar crew misidentified it as an attacking Iranian fighter jet. All 290 people on board were killed. That tragedy is why training, protocols, and human judgment remain at the center of air defense, no matter how sophisticated the radar becomes. The technology is the tool. The judgment is everything. So there you have it. From the moment a foreign aircraft appears on a radar screen to the moment an intercept is made, every second matters. Every layer of technology, every protocol, every human decision is part of a system designed to protect airspace and prevent miscalculations from becoming catastrophes. Military radar isn't just a machine. It's a network of technology, training, and human judgment that operates 24 hours a day, 7 days a week, in countries all over the world. If you found this video valuable, please hit the like button. It genuinely helps more people find this content. If you want more deep dives into military technology, defense systems, and the science behind modern warfare, subscribe. We cover this stuff every week, and drop a comment below. What topic should we break down next?